One of the most beautiful results in the theory of integer partitions, probably the most, is Euler's pentagonal number theorem. So why is it called pentagonal number theorem? Well, these are the pentagonal numbers. They're generalizations of the triangle numbers and the square numbers, and you'll have a homework problem to make you a little more comfortable with those numbers. And what does this have to do with partitions? Well, for that, let's look at the proof. So for the proof, what I want to start out doing, actually, I'll start out with the right-hand side. And let's expand this out. So summing over integers is a little bit annoying. So let's sum over the natural numbers. And actually, let's pull off 1. And then we can fold the rest of the terms together. So now I'm going to fold and say, okay, n greater than or equal to 1. And I'm going to put the positive and negative terms together. So I can still take -1 to the n because -5 and 5 have the same parity. And now when I take the positive n, I'm going to get n 3n minus 1 over 2. Plus, and now let's just do an exercise. If we take minus n and we take minus 3n minus 1 over 2, well, we can pull out the minus sign for the n and for the minus 3n minus 1, and we just get this. So we get plus x to the n, 3n plus 1 over 2. So that's kind of nice. It's telling us that this expansion, the sum over z, what does it look like? Well, it's all multiplicity free. And we only get certain exponents. So maybe to make this a little more concrete, let's just write it out. So we're going to get, I guess we'll get a negative term first. Negative x minus x squared. So the terms kind of come in pairs for the positive and negative. So that's what we get when we put in n equal 1. For n equal 2, we're going to get x to the 5 and x to the 7. And now for n equals 3, we're going to get 12 and 15. For n equals 4, we're going to get 22 and 26. And then keep going like that. Okay, so notice that the right-hand side is multiplicity free, meaning that the coefficients are all plus or minus 1 or 0. So that's kind of interesting. So now let's go and prove this. And then we'll see where the partitions come into play. So as we write down the proof, the partitions that we're going to be interested in are going to be partitions into distinct parts, which often we've been using the letter Q to denote. So these are partitions lambda of n such that lambda I is not equal to lambda j for any I that's not equal to j. Okay, and we know what the generating function for those is. We've done that before. So the generating function is just the infinite product of 1 plus x to the k. But notice that up here we have 1 minus x to the k. So what is that doing? Well, that's telling us the product k greater than or equal to 1 of 1 minus x to the k is equal to the sum n greater than or equal to 0 of, let's say, f of n, x to the n. It's the generating function of something, of what? Well, f of n is equal to the sum of partitions in Q of n. So we're counting these partitions with a parity based on the length of the partition. Because if you think about how many terms you take, that's exactly going to give you how many negative signs you get. And the number of terms is the length of the partition. So this is telling us there's sort of, it's the number of terms of even length minus the number of terms of odd length. And so that's exactly what has to be on the right-hand side. So what we want to show in order to prove this theorem is that f of n, this thing that counts combinatorially the left-hand side, also counts the right-hand side, but we know what the right-hand side looks like. So we want to show that f of n is equal to, and unfortunately I chose n, so now I have to switch and choose k, but I think I can handle it, is minus 1 to the k or 0. And it's this whenever we have something of the form 3k plus or minus 1 over 2, and it's 0 otherwise. Okay? So that's what we're trying to show. That's kind of a bizarre thing. So we have this combinatorial interpretation of Fn. It's maybe another way to write it is f of n is equal to the number of partitions lambda in Q of n, such that the length of lambda is even, minus the number of lambda in Q of n, should be an n, such that the length of lambda is odd. Okay, and we want to show, so that's what we know, and this is what we need to show. And now how are we going to do that? Well, we're going to do that with what's called a sign reversing involution. And the right way to think of this, so we're going to have this map phi that I'm going to attempt to define on Q of n to itself. I want phi squared to be the identity, and I want it to be the case that the length of phi of lambda is not the same mod 2 as the length of lambda. So it needs to change the parity. And if I can do that, that's basically going to cancel out these terms that we get here. So it's going to cancel the even terms with the odd terms. And I'm going to be able to do it in this case, and I'm not going to be able to do it in this case. I'm going to have one thing left over, and it's going to have positive or negative sign. So let's see how that goes. I think it's easiest to see once we just throw out an example. So here is an example. So this is a partition into distinct parts. I'm going to think about two different values here. I'm going to think about this value here, which I'm going to call d of lambda. In this particular case, d lambda equals 3. So d lambda is equal to the maximum index I such that lambda I is equal to lambda 1 minus I plus 1. Okay, so the number of times you decrease by 1. As you start at the bottom, you go down by 1, and when you have a gap of more than 1, you stop, and that's the end. Okay, so d lambda could be 1, or it could be the whole thing. Okay, but we certainly decrease by at least 1, so we know that that's going to happen. All right, that's one value that I want to consider. Another value that I want to consider, maybe it'll be blue, is going to be the length of the last part. So we're just going to call this L sub lambda equals lambda sub length of lambda. Maybe L sub lambda is not less cumbersome, but maybe it is. Okay? So these are the two values I care about, and this is how my map is going to go. Let's go ahead and write it down. So phi of lambda. There are going to be two cases. So one case, and I'll write my if first. So if d of lambda is strictly smaller than L, well, I guess let me be consistent with my notation. I'm subscripting. So if d sub lambda is strictly less than L sub lambda, then I'm going to do one thing, and if L sub lambda is greater than or equal to, less than or equal to d sub lambda, then I'm going to do something else. So let me show you the something else case, because I think we're in the case where d sub lambda is bigger in this, for this example. So here's my example done again. So I compare, and I've got L sub lambda is smaller. Let's bring L sub lambda back here. So what I'm going to do in this particular case is I'm going to take L sub lambda, I'm going to remove it and stick it down here and make it line up on the holes. So let's see if I can do this. Great. That's what I'm going to do. So let me try to write that down in words. So in this case, you're going to remove lambda sub L of lambda. You're going to remove the last part, and you're going to add 1 to lambda 1 all the way up to whatever you need to add it up to. Okay? So however many you've taken off, that's how many you add to. And in the other case, I'm going to reverse this. So when d lambda is small enough, then I can sort of, I can undo it, right? I can just take this off and I could put this back on the top. So that's what I'm going to do here. You're going to remove 1 from lambda 1 all the way up to lambda d sub lambda. And you're going to add a part of size d sub lambda to the end. That's my map. A big question you can ask yourself, is this well-defined? And that's something you always need to ask when you're creating a bijection. And the answer is not always. Well, how can it go wrong? That's what we really want to think about. We want to think about, okay, how could it possibly go wrong? I'll maybe stick with red. So one way that it could go wrong is if I have this partition here, let's see. Okay, suppose I have a partition like this, and I'm going to look now at, here's my d sub lambda, and here's my L lambda, okay? So in this case, I come up in my map and I say, okay, well, d lambda is 3 and L lambda is 3, so I should be removing the last part and adding it. So when I try to do that, what's going to happen? I'm going to end up with these guys staying the same, and now I have this blue line that I had here, except that last guy gets taken off, and now I'm trying to add something of length 3. So I'm trying to add this. And I've sort of crippled myself here, right? This is what the map phi would want to do, and that's no good. So when does this actually happen? For what partitions could this possibly happen? Well, this is going to be the case where I have something of the form, let's see, 2k minus 1, 2k minus 2, a staircase that takes me all the way to the top ending in k, because in this case, I get that d lambda, or rather d mu, is going to be equal to k, and L mu is going to also be equal to k. And when they're both equal to k, then the problem is that when I start to take off that L mu and I take off that last part, I've also taken off a little bit of d mu. And that's a problem. And the problem comes in two flavors. So it comes like this, but we're also going to have the problem if we start with something that's 2k minus 1, and takes us all the way down to k plus 1. This is going to have the same problem, except that it's going to be slightly different. In this case, we're going to have d mu is going to equal k minus 1. Oh, sorry, it's going to equal k. Same thing there. But L mu is going to equal k plus 1. This is going to end up with the same problem, and this is really the same example, except, let's see, we'll copy that guy, paste it back. It's mostly the same example, except I just sort of add this extra row to the back. And then I'm lengthening that, which apparently I've reversed my colors there, but hopefully you'll forgive me. And so now we would be taking off this, let's see, we'll think about what's happening here. We're going to want to take this piece off. So I guess I need to actually scoot everybody down so that I can do that. We'll take this piece off. And then we're going to rotate it and try to stick it on top. And now we're kind of in trouble. Probably because I can't draw. Because now we have two parts that are the same size. Okay, so here we got a problem because we're adding one to, and there's nowhere to put it. And here we have another problem. And these are the only two ways that it could go wrong. So if you think about that for a little bit, this is the only way that it could go wrong. And now we can ask ourselves, well, what is the size of mu? And the size of mu in this case is going to be k times 3k minus 1 over 2. And what's the size of nu? It's equal to k 3k plus 1 over 2. And so these are what we're going to call our fixed points. So we're actually not going to define the map phi up here. We're going to define the map phi except for these two partitions. So if n is not equal to k times 3k plus or minus 1 over 2, then we'll define it. Otherwise, we're going to define the map on q of n minus mu or minus nu, whichever case applies. And if you see here that what's the length? The length in both of these cases is k. So we have exactly k parts. And so the length is k, so we're exactly going to get this minus 1 to the k showing up is how we're going to count it. And this is the one fixed point that we have. So this is an example of what's called a sign reversing involution. And this is a powerful technique whenever in combinatorics, whenever we want to prove something that sort of has this alternating flavor. And this completes the proof. So we have this bijection, which tells us that, okay, all the terms are going to cancel unless I am in the case where one of these two, mu or nu, applies. And in that case, I get one thing left over, and it's going to have the correct parity. So that is the proof